विद्यार्थियों, ਮੰਨ ਲਓ ਕਿ ਇੱਕ ਸਰਕੂਲਰ ਸ਼ੇਪ ਦੀ ਆਬਜੈਕਟ ਇੱਕ ਸਕਰੂ ਦੀ ਸਹਾਇਤਾ ਨਾਲ ਕੰਧ ਤੇ ਲਟਕਾਈ ਗਈ ਹੈ। ਮੰਨ ਲਓ ਕਿ ਇਸ ਤੇ ਫੋਰਸ F ਲੱਗ ਰਹੀ ਹੈ ਅਤੇ ਇਸ ਦੇ ਕਾਰਨ ਇਹ ਸਵਿੰਗ ਕਰਨਾ ਸ਼ੁਰੂ ਕਰਦੀ ਹੈ ਅਤੇ ਇਹ ਰੋਟੇਸ਼ਨਲ ਮੋਸ਼ਨ ਵਿੱਚ ਹੈ। ਕੀ ਤੁਸੀਂ ਜਾਣਦੇ ਹੋ ਕਿ ਇਸ ਤੇ ਕਿੰਨੀ ਫੋਰਸ ਲੱਗ ਰਹੀ ਹੈ? ਕਿੰਨਾ ਕੰਮ ਹੋਇਆ ਹੈ? ਜਾਂ ਸਰਕੂਲਰ ਆਬਜੈਕਟ ਦੇ ਉੱਪਰ ਕਿੰਨੀ ਪਾਵਰ ਲਗਾਈ ਗਈ ਹੈ? ਤੁਹਾਨੂੰ ਇਹਨਾਂ ਸਾਰੇ ਸਵਾਲਾਂ ਦੇ ਜਵਾਬ ਅੱਜ ਦਾ ਵਿਸ਼ਾ ਪੜ੍ਹਨ ਤੋਂ ਬਾਅਦ ਜਾਣ ਜਾਓਗੇ।
ਵਿਦਿਆਰਥੀਓ, ਤੁਹਾਡਾ ਅੱਜ ਦੀ ਕਲਾਸ ਡਾਇਨਾਮਿਕਸ ਆਫ ਰੋਟੇਸ਼ਨਲ ਮੋਸ਼ਨ ਵਿੱਚ ਸਵਾਗਤ ਹੈ। ਪਹਿਲਾਂ ਅੱਜ ਦੇ ਸਿੱਖਿਆ ਉਦੇਸ਼ਾਂ ਨਾਲ ਸ਼ੁਰੂ ਕਰਦੇ ਹਾਂ।
On completion of this topic, learners will be able to derive expression for work done by torque during rotational motion, derive expression for instantaneous power of rotational motion, derive expression for angular momentum due to rotational motion, derive expression for kinetic energy due to rotational motion. Discuss Newton's second law of motion in rotational motion.
ਰੋਟੇਸ਼ਨਲ ਮੋਸ਼ਨ ਦੇ ਕਾਈਨੈਮੈਟਿਕਸ ਨੂੰ ਪੜ੍ਹਨ ਤੋਂ ਬਾਅਦ ਹੁਣ ਅਸੀਂ ਰੋਟੇਸ਼ਨਲ ਮੋਸ਼ਨ ਦੇ ਡਾਇਨਾਮਿਕਸ ਦੇ ਵਿਸ਼ੇ ਵਿੱਚ ਵੀ ਜਾਣਾਂਗੇ। ਤੁਸੀਂ ਸਾਰੇ ਹੀ ਜਾਣਦੇ ਹੋ ਕਿ ਪਾਰਟੀਕਲਸ ਦੇ ਸਿਸਟਮ ਦਾ ਸੈਂਟਰ ਆਫ ਮਾਸ ਸਿਰਫ ਸਿਸਟਮ ਨੂੰ ਬਣਾਉਣ ਵਾਲੇ ਪਾਰਟੀਕਲਸ ਦੀ ਪੋਜੀਸ਼ਨਸ ਅਤੇ ਮਾਸਸ ਦਾ ਇੱਕ ਫੰਕਸ਼ਨ ਹੈ। ਰਿਜਿਡ ਬਾਡੀਜ਼ ਦੇ ਕੇਸ ਵਿੱਚ ਇਸ ਦੇ ਸੈਂਟਰ ਆਫ ਮਾਸ ਦੀ ਪੋਜੀਸ਼ਨ ਵਿਦ ਰਿਸਪੈਕਟ ਟੂ ਦ ਆਬਜੈਕਟ ਫਿਕਸਡ ਹੁੰਦੀ ਹੈ, ਪਰ ਇਹ ਜ਼ਰੂਰੀ ਨਹੀਂ ਕਿ ਇਹ ਇਸ ਨਾਲ ਕੰਟੈਕਟ ਵਿੱਚ ਹੋਵੇ। ਪਹਿਲਾਂ ਅਸੀਂ ਰੋਟੇਸ਼ਨ ਨੂੰ ਡਿਸਕ੍ਰਾਈਬ ਕਰਨ ਲਈ ਯੂਜ਼ਫੁਲ ਕੁਝ ਫਿਜ਼ੀਕਲ ਕੁਆਂਟੀਟੀਜ਼ ਬਾਰੇ ਪੜ੍ਹਿਆ ਸੀ। ਐਂਗੂਲਰ ਡਿਸਪਲੇਸਮੈਂਟ ਥੀਟਾ ਨੂੰ ਰੇਡੀਅਨਸ ਵਿੱਚ ਮਾਪਿਆ ਜਾਂਦਾ ਹੈ ਅਤੇ ਇਹ ਮੀਟਰਸ ਵਿੱਚ ਮੈਜਰ ਕੀਤੇ ਜਾਣ ਵਾਲੇ ਲੀਨੀਅਰ ਡਿਸਪਲੇਸਮੈਂਟ ਦੇ ਐਨਾਲੋਗਸ ਹੈ। ਐਂਗੂਲਰ ਵੈਲੋਸਿਟੀ ਓਮੇਗਾ ਰੇਡੀਅਨਸ ਪਰ ਸੈਕਿੰਡ ਵਿੱਚ ਮਾਪੀ ਜਾਂਦੀ ਹੈ। ਇਹ ਲੀਨੀਅਰ ਵੈਲੋਸਿਟੀ ਦੇ ਐਨਾਲੋਗਸ ਹੈ ਜਿਹੜੀ ਮੀਟਰਸ ਪਰ ਸੈਕਿੰਡ ਵਿੱਚ ਮੈਜਰ ਕੀਤੀ ਜਾਂਦੀ ਹੈ। ਇਸੇ ਤਰ੍ਹਾਂ ਐਂਗੂਲਰ ਐਕਸਲਰੇਸ਼ਨ ਅਲਫਾ ਰੇਡੀਅਨਸ ਪਰ ਸੈਕਿੰਡ ਸਕੁਆਇਰ ਵਿੱਚ ਮੈਜਰ ਕੀਤੀ ਜਾਂਦੀ ਹੈ ਅਤੇ ਲੀਨੀਅਰ ਐਕਸਲਰੇਸ਼ਨ ਦੇ ਐਨਾਲੋਗਸ ਹੈ ਜਿਸ ਨੂੰ ਕਿ ਮੀਟਰਸ ਪਰ ਸੈਕਿੰਡ ਸਕੁਆਇਰ ਵਿੱਚ ਮੈਜਰ ਕੀਤਾ ਜਾਂਦਾ ਹੈ। Just as force, which is measured in Newton, played a huge role in linear dynamics, we have torque, tau, measured in Newton meters in rotational dynamics. We begin by defining this quantity and showing how it acts on objects in rotational motion. Next, we relate torque to a study of kinematics through an equation very similar to Newton's second law. In addition, we will develop concepts of work, kinetic energy and power similar to those in linear motion. I will like to begin with the definition of torque.
A man is trying to open the door by applying some force on the edge of the door. Here, the point of application of force is at some distance from the hinges of the door. So, here a torque is experienced by the door.
Hence, torque is the product of force and perpendicular distance. It is denoted by the symbol tau. Mathematically, we can write tau equal to r into f, where r is the perpendicular distance between the point of application and the boundary of the object, while f is the amount of force applied. Let us now try to calculate the work done by a torque in case of rotational motion. ਇਹ ਜਾਣਨ ਲਈ ਕਿ ਰੋਟੇਸ਼ਨਲ ਮੋਸ਼ਨ ਦੇ ਕੇਸ ਵਿੱਚ ਵਰਕ ਨੂੰ ਕਿਸ ਤਰ੍ਹਾਂ ਮੈਜ਼ਰ ਕੀਤਾ ਜਾਂਦਾ ਹੈ, ਆਓ ਇਹ ਵੀਡੀਓ ਦੇਖਦੇ ਹਾਂ।
ਮੰਨ ਲਓ ਇੱਕ ਬੋਲਟ ਨੂੰ ਟਾਈਟ ਕਰਨ ਲਈ ਇੱਕ ਰੈਂਚ ਦੀ ਵਰਤੋਂ ਕੀਤੀ ਗਈ ਹੈ। ਜਿਉਂ ਹੀ ਰੈਂਚ ਬੋਲਟ ਨੂੰ ਫੜਦਾ ਹੈ ਤਾਂ ਇਹ ਮਜ਼ਬੂਤੀ ਨਾਲ ਉਸ ਨੂੰ ਜਕੜ ਲੈਂਦਾ ਹੈ। ਜਦੋਂ ਫੋਰਸ F ਰੈਂਚ ਦੇ ਹੈਂਡਲ ਤੇ ਲੱਗਦੀ ਹੈ ਤਾਂ ਇਹ ਕੁਝ ਐਂਗਲ ਡੈਲਟਾ ਥੀਟਾ ਦੇ ਨਾਲ ਕਲੌਕਵਾਈਜ਼ ਡਾਇਰੈਕਸ਼ਨ ਵਿੱਚ ਰੋਟੇਟ ਕਰਦਾ ਹੈ ਅਤੇ ਇਸ ਕਰਕੇ ਬੋਲਟ ਟਾਈਟ ਹੋ ਜਾਂਦਾ ਹੈ। ਇਸ ਤੋਂ ਸਿੱਧ ਹੁੰਦਾ ਹੈ ਕਿ ਬੋਲਟ ਨੂੰ ਟਾਈਟ ਕਰਨ ਲਈ ਇਸ ਰੋਟੇਸ਼ਨਲ ਮੋਸ਼ਨ ਵਿੱਚ ਕੁਝ ਕੰਮ ਹੋਇਆ ਹੈ।
ਕੀ ਤੁਸੀਂ ਵੇਖਿਆ ਕਿ ਰੈਂਚ ਦੁਆਰਾ ਕਿਸ ਤਰ੍ਹਾਂ ਟਾਰਕ ਨੇ ਆਪਣਾ ਰੋਲ ਪਲੇ ਕੀਤਾ ਅਤੇ ਕਿਸ ਤਰ੍ਹਾਂ ਬੋਲਟ ਟਾਈਟ ਹੋ ਗਿਆ। Let us now derive a mathematical expression for the work done by the wrench during rotational motion. Let us consider that the force F, which is applied on the bolt, is a combination of infinite number of forces acting on the bolt. Let these forces be F1, F2, F3 and so on. Suppose that these forces exert torques tau 1, tau 2, tau 3 and so on the body, and as a result the body rotates through an infinitesimally small angle d theta about a given axis of rotation. The displacement of particle P1 of the rigid body is under the effect of force F1 through an angle d theta. The particle moves along a circular arc P1 P1 dash of radius r1. Since the angular displacement d theta is infinitesimally small, the distance moved by the particle along the circular arc can be taken as approximately straight. Therefore, work done in rotating the particle P1 through an angle d theta is given by dw1 equal to f1 into p1 p1 dash, which is equal to f1 into r1 d theta. Since the torque acting on the body is tau 1 equal to f1 into r1, the work done in rotating the particle p1 is dw1 equal to tau 1 into d theta. Similarly, work done by the other torques are given by dw2 equal to tau 2 into d theta, dw3 equal to tau 3 into d theta and so on. Therefore, total work done in rotating the body dw is equal to dw1 plus dw2 plus dw3 and so on. This gives dw equal to tau 1 into d theta plus tau 2 into d theta plus tau 3 into d theta and so on. Or dw is equal to tau 1 plus tau 2 plus tau 3 plus so on whole into d theta. Since all the torques are along the axis of rotation, the magnitude of the total torque acting on the body is just equal to the algebraic sum of the magnitudes of the torques. In other words, tau is equal to tau 1 plus tau 2 plus tau 3 and so on. Or dw is equal to tau into d theta. Thus, we conclude that work done by a torque in rotational motion is analog to the work done by a force in linear motion. This simply means that dw is equal to F into ds. Let us now find out the instantaneous power in rotational motion. ਤੁਸੀਂ rotational motion ਦੌਰਾਨ ਟਾਰਕ ਰਾਹੀਂ ਹੋਏ ਵਰਕ ਦੇ ਕਨਸੈਪਟ ਨੂੰ ਸਮਝ ਲਿਆ ਹੈ। ਤੁਸੀਂ ਜਾਣਦੇ ਹੋ ਕਿ ਟਾਈਮ ਰੇਟ ਆਫ ਚੇਂਜ ਆਫ ਵਰਕ ਡਨ ਨੂੰ ਪਾਵਰ ਕਿਹਾ ਜਾਂਦਾ ਹੈ। ਚਲੋ ਹੁਣ ਵੇਖੀਏ what is the term instantaneous power in rotational motion।
ਮੰਨ ਲਓ ਕਿ ਇੱਕ ਮੁੰਡਾ ਬਾਈਸਿਕਲ ਦੇ ਪੈਡਲ ਉੱਪਰ ਫੋਰਸ F ਲਾਉਂਦਾ ਹੈ, ਜਿਸ ਕਾਰਨ ਸਾਈਕਲ ਦਾ ਪਹੀਆ ਐਂਟੀ ਕਲੌਕਵਾਈਜ਼ ਡਾਇਰੈਕਸ਼ਨ ਵਿੱਚ ਰੋਟੇਟ ਹੋਣਾ ਸ਼ੁਰੂ ਹੋ ਜਾਂਦਾ ਹੈ। ਮੰਨ ਲਓ ਕਿ ਟਾਈਮ ਡੈਲਟਾ t ਵਿੱਚ ਸਾਈਕਲ ਦਾ ਪੈਡਲ ਕੁਝ ਐਂਗਲ ਡੈਲਟਾ ਥੀਟਾ ਨਾਲ ਰੋਟੇਟ ਹੋ ਜਾਂਦਾ ਹੈ। ਇਸ ਤੋਂ ਇਹ ਪਤਾ ਲੱਗਦਾ ਹੈ ਕਿ ਇੱਥੇ ਇੱਕ ਮੁੰਡੇ ਵੱਲੋਂ ਸਾਈਕਲ ਦੇ ਪੈਡਲ ਉੱਤੇ ਕੁਝ ਫੋਰਸ ਲਾਉਣ ਨਾਲ ਕੰਮ ਹੋਇਆ ਹੈ, ਕਿਉਂਕਿ ਪੈਡਲ ਦੇ ਉੱਪਰ ਹਰ ਸਮੇਂ ਕੀਤਾ ਗਿਆ ਕੰਮ ਬਦਲ ਰਿਹਾ ਹੈ। ਇਸ ਕਰਕੇ ਪੈਡਲ ਉੱਪਰ ਕੁਝ ਪਾਵਰ ਲਾਈ ਗਈ ਹੈ, ਜਿਸ ਨੂੰ ਇੰਸਟੈਂਟੇਨੀਅਸ ਪਾਵਰ ਕਿਹਾ ਜਾਂਦਾ ਹੈ।
Here, the total work done in rotating the body is dw equal to tau into d theta. On dividing both sides by dt, we get dw by dt equal to tau into d theta by dt. This implies P is equal to tau into omega. We conclude that instantaneous power in rotational motion is analog to the instantaneous power in linear motion, as P is equal to F into V. आओ ਹੁਣ ਇਹ ਵੇਖੀਏ ਕਿ ਇੱਕ ਬੋਡੀ ਜਿਹੜੀ rotational motion ਵਿੱਚ ਹੈ ਉਸ ਉੱਤੇ ਟਾਰਕ ਕੀ ਹੋਵੇਗੀ।
Let a force F applied on the paddle of the bicycle, due to which the wheel of the cycle get rotated in anti-clockwise direction. Due to the rotation of the wheel, it acquires some angular velocity omega and hence angular acceleration alpha. Hence, the moving wheel having some moment of inertia and angular acceleration experiences a torque tau.
ਤੁਹਾਨੂੰ ਪਤਾ ਹੀ ਹੈ ਕਿ work done by the applied torques bring about an increase in its kinetic energy of rotation. Obviously, the instantaneous power is equal to the rate of increase of the kinetic energy of rotation of the body, or P is equal to d by dt of 1 by 2 into I omega square. This gives P is equal to 1 by 2 into I into 2 omega d omega by dt, which is equal to I into omega into alpha. Since the instantaneous power in rotational motion is P is equal to tau into omega, or tau into omega is equal to I omega into alpha, which is equal to I alpha. Here we conclude that torque in rotational motion is analog to the expression for force in linear motion, that is F is equal to m into a. ਹੁਣ ਵੇਖਦੇ ਹਾਂ ਕਿ rotating body ਦਾ angular momentum ਕੀ ਹੁੰਦਾ ਹੈ।
Let a man holding some weights in both hands sitting on a rotating chair. Let he pulls his both hands away from the chest and start rotating. During rotation, he attained some angular velocity and hence some angular momentum. Here, the man is rotating in such a way that his body is pointing in z direction perpendicular to the xy plane.
Let us now find a mathematical expression for angular momentum of rotating body, for which we consider a plain rigid body consisting of n particles having masses m1, m2, m3 and so on up to Mn, located at points whose position vectors are vector r1, vector r2, vector r3 and so on respectively, oriented in a plane and rotating with angular velocity vector omega about the axis OZ in anticlockwise direction. The other two coordinate axes OX and OY lie in the plane of the rigid body. Let ith particle of mass mi be located at the point P whose position vector is vector ri. As the plane rigid body rotates about the axis OZ, the constituent particles will move along transverse circular paths. The ith particle will follow a path of radius vector ri, whose linear velocity is given by vector vi equal to vector omega cross vector ri. The angular momentum of the ith particle about the axis OZ is given by vector li equal to vector ri cross mi into vector vi, or vector li is equal to vector ri cross mi into vector omega cross vector ri, which is equal to mi into vector ri cross vector omega cross vector ri. Since vector a cross vector b cross vector c is equal to vector a dot vector c into vector b minus vector a dot vector b into vector c. So, we get angular momentum of the ith particle about the axis OZ as vector li equal to mi into whole of vector ri dot vector ri into vector omega minus vector ri dot vector omega into vector ri. Since the radius vector ri is perpendicular to the angular velocity vector omega, therefore, we have vector ri dot vector omega equal to 0, which gives vector li equal to mi into ri square into vector omega. The total angular momentum of the plane lamina about the axis OZ is vector L equal to summation function I equal to 1 to n vector Li, which is also equal to summation function I equal to 1 to n mi into ri square into vector omega. This gives summation function I equal to 1 to n mi into ri square into vector omega. Summation function I is equal to 1 to n mi into ri square equal to I, implies vector L is equal to I into vector omega. Here, I is the moment of inertia of the rigid body about the axis OZ. So, we conclude that the angular momentum is analogous to the linear momentum, or mathematically vector P is equal to m into vector v. ਤੁਹਾਨੂੰ याद ही होवेगा that every rotating body possesses some kinetic energy and also some external torque is always acting on it. So आओ पहला ये देखते हैं कि what is the kinetic energy possessed by a rotating body.
Consider an object of mass m is connected with a thread of length say r. As it starts rotating around its axis, it attains some linear velocity v and hence some angular velocity omega. This rotating body have some moment of inertia, say I, and angular velocity omega, which help in imparting some kinetic energy to the object.
Let us now find a mathematical expression for kinetic energy of a rigid body rotating about its axis. To do this, let us consider that the kinetic energy of ith particle of object due to rotation about the axis is Ti equal to 1 by 2 into mi vi square. The magnitude of the linear velocity of the ith particle will be vi equal to ri into omega, or Ti is equal to 1 by 2 into mi ri into omega whole square, which is equal to 1 by 2 into mi ri square into omega square. Therefore, the total kinetic energy of the rotation of the plane lamina about the axis OZ is T equal to summation function I equal to 1 to n Ti, which is equal to summation function I equal to 1 to n 1 by 2 into mi ri square into omega square. This is equal to 1 by 2 into whole of summation function I equal to 1 to n mi into ri square into omega square. This becomes equal to 1 by 2 into I into omega square. Here we conclude that kinetic energy of rotation is analogous to the kinetic energy of translational motion, or mathematically T is equal to 1 by 2 into m into v square. We have studied linear motion with the help of Newton's laws. However, rotational dynamics cannot be studied with the help of Newton's laws of linear motion. Instead, we try to develop parallel concepts to those of linear dynamics. Anyhow, the study of rotational dynamics contains unique concepts and equations. ਤੁਸੀਂ ਸਾਰੇ ਹੀ ਨਿਊਟਨਸ ਸੈਕੰਡ ਲਾਅ ਆਫ ਮੋਸ਼ਨ ਇਨ ਕਾਈਨੈਮੈਟਿਕਸ ਨਾਲ ਫੈਮਿਲੀਅਰ ਹੋ। ਹੁਣ ਅਸੀਂ ਇਸ ਦੇ ਕਾਊਂਟਰਪਾਰਟ ਨਿਊਟਨਸ ਸੈਕੰਡ ਲਾਅ ਆਫ ਮੋਸ਼ਨ ਇਨ ਰੋਟੇਸ਼ਨਲ ਮੋਸ਼ਨ ਬਾਰੇ ਜਾਣਾਂਗੇ। ਆਓ ਵੇਖੀਏ what does the Newton's second law of motion in rotational motion conveys. As we know that the total angular momentum of the rotating body, which has an angular velocity as vector omega and moment of inertia I as vector L, is equal to I into vector omega. Differentiating both sides with respect to t, we get d vector L by dt is equal to I into d vector omega by dt. Since d vector L by dt is equal to vector tau and d vector omega by dt is equal to vector alpha, it implies that vector tau is equal to I into vector alpha, which expresses Newton's second law in rotational motion. Thus, we conclude that Newton's second law in rotational motion is analog of the mathematical form of Newton's second law in linear motion. Mathematically, vector f is equal to d vector p by dt. Therefore, from this discussion, it follows that in the expressions for rotational motion, where the linear velocity v of the body is replaced by angular velocity omega, linear momentum p by angular momentum L, force F by torque tau, the mass m is replaced by moment of inertia I of the body. Hence, moment of inertia plays the same role in rotational motion as mass does in translational motion. After having understood the dynamics of rotational motion, let's solve a numerical problem based on it. Energy of 600 joules is spent in increasing the speed of a flywheel from 300 revolutions per minute to 420 revolutions per minute. Find the moment of inertia of the wheel. Here, total energy spent is T equal to 600 joules. Initial speed of the wheel is nu1 equal to 300 revolution per minute, and final speed of revolution is nu2 equal to 420 revolutions per minute. Now, the speed of the wheel per second is nu1 equal to 300 revolutions per minute, which is equal to 5 revolutions per second, and final speed of revolution is nu2 equal to 420 revolutions per minute, which is equal to 7 revolutions per second. Since the formula of angular speed of the rotating body is omega equal to 2 pi nu. Now, substituting the value of nu1 and nu2 in the given formula, we get the initial angular velocity of the rotating wheel as omega 1 equal to 2 pi into 5, which is equal to 10 radian per second, and the final angular velocity of the rotating wheel as omega 2 equal to 2 pi into 7, which is equal to 14 radians per second. Let I be the moment of inertia of the wheel. Therefore, the initial rotational kinetic energy of the flywheel is Ti equal to 1 by 2 into I into omega 1 square, which is equal to 1 by 2 into I into 10 pi whole square, which is equal to 1 by 2 into I into 100 pi square, which is 50 pi square into I. And the final rotational kinetic energy of the flywheel is Tf equal to 1 by 2 into I into omega 2 square equal to 1 by 2 into I into 14 pi whole square, which is equal to 1 by 2 into I into 196 pi square, which is equal to 98 pi square into I. Now, increase in rotational kinetic energy of the flywheel is equal to the energy spent in increasing the speed of the flywheel. Using this theory, we get Tf minus Ti as equal to T. Now, substituting the values of Tf, Ti and T in the given formula, we get 98 pi square into I minus 50 pi square into I as equal to 600, or 48 pi square into I is equal to 600. On solving, we get the value of I as equal to 600 by 48 pi square, which is equal to 25 into 7 into 7 upon 2 into 22 into 22, which is again equal to 1.26 kilogram meter square. विद्यार्थियों, आओ जो कुछ आपा हुण तक पढ़िया है उसका सार कर लिए. The expression for work done by a torque in rotational motion is analog of the expression for work done by a force in linear motion. The expression for instantaneous power in rotational motion is analog of the expression for instantaneous power in linear motion. The expression for torque in rotational motion is analogous to the expression for force in linear motion. ਅਸੀਂ ਅੱਜ ਦੇ ਪਾਠ ਦੇ ਅੰਤ ਤੇ ਪਹੁੰਚ ਗਏ ਹਾਂ. ਹੁਣ ਕੁਝ ਸਵਾਲ ਪੁੱਛ ਕੇ ਇਹ ਪਤਾ ਕਰਦੇ ਹਾਂ ਕਿ ਤੁਸੀਂ ਅੱਜ ਦੇ ਪਾਠ ਵਿੱਚੋਂ ਕੀ ਕੁਝ ਸਿੱਖਿਆ ਹੈ. My first question is, what is angular momentum? The answer is, the turning movement of a particle about the axis of rotation is called the angular momentum of the particle. The next question is, what is the relation between kinetic energy and moment of inertia if the body is moving with unit angular velocity? The answer is, moment of inertia is equal to twice the kinetic energy. Another question, does moment of inertia change with the change of the axis of rotation? The answer to this is yes. Moment of inertia changes with the change of the axis of rotation. ਮੈਨੂੰ ਪੂਰਾ ਯਕੀਨ ਹੈ ਕਿ ਤੁਸੀਂ ਅੱਜ ਦਾ ਇਹ ਪਾਠ ਬੜੇ ਧਿਆਨ ਨਾਲ ਸੁਣਿਆ ਹੋਵੇਗਾ ਅਤੇ ਇਸ ਤੋਂ ਕੁਝ ਸਿੱਖਿਆ ਵੀ ਹੋਵੇਗਾ। ਆਸ ਹੈ ਕਿ ਤੁਸੀਂ ਹੁਣੇ ਹੀ ਪੁੱਛੇ ਗਏ ਸਵਾਲਾਂ ਦੇ ਉੱਤਰ ਚੰਗੀ ਤਰ੍ਹਾਂ ਜਾਣ ਗਏ ਹੋ। ਧਿਆਨ ਦੇਣ ਲਈ ਧੰਨਵਾਦ। ਅਗਲੀ ਕਲਾਸ ਵਿੱਚ ਫਿਰ ਮਿਲਾਂਗੇ। ਤਦ ਤੱਕ ਬਹੁਤ ਸਾਰੀਆਂ ਸ਼ੁਭਕਾਮਨਾਵਾਂ।